Morning, Bill. Morning, Molly. Good morning, Michaela. Morning, Jimmy. Make sure I'm recording. I think I am. There we go. People still coming in. Bill, did you ever figure out that example?
Been working on it yesterday and today, but I still can't get it.
Oh, did you see that I sent you a Zoom invitation?
Yes, but I was working on the chemistry Pearson, and I didn't see it.
Oh, no problem.
We're too late.
We were jinxed yesterday, I think, or this
Yeah.
week. And it was 13.7, right?
Yes, it was the Skill Builder Plus 13.7.
Okay, well, so while people are coming in, why don't we just do it?
Okay. I
Let me
think I was on the right track with it, but I just can't seem to get over that last hurdle.
Well, I think it might wind up being a factor of 2 because of,
It is a factor of 2. I
yeah.
didn't know how to get the 2 into the equation.
Okay, I'm gonna try to change my share. So you guys see my camera now?
Yeah.
Yeah, okay. All right, so this is on page 462 of the book. And it's example 13.7. And I'm going to continue to let people into the meeting while I do this. Okay, so it's a reaction between potassium iodide and lead nitrate, lead 2 nitrate. And a precipitate, lead iodide, is produced in solid form and potassium nitrate. And we are told that we have a volume of 0.104 liters of the lead nitrate and 0.225 molar lead nitrate. And if it's going to react with 0.115 molar potassium iodide, how much potassium iodide do we need to have this react completely? Okay, now one thing I want to remind you guys is that big M stands for moles or liters of solution. And so so another way of looking at the 0.225 molar is to say that there are 0.225 moles of lead nitrate, in 1 liter of solution. And from that equivalence, we can make conversion factors. Okay, so yeah,
Professor,
yeah,
is that Skill Builder 13.7, page 462?
yeah. Oh, skill builder, the one below it. Oh, okay. You want me to do that one instead?
Yeah, Skill Builder Plus.
Okay. Yeah, let's do that. Because this one you have the solution in your book.
Right. Yes.
Sorry, I didn't hear the skill builder part,
And
or I didn't notice it. Okay,
one more
so
question, Professor. On that
yeah.
particular problem, does that chemical equation still apply down there for the Skill Builder Plus? Or is that a different problem
For the
totally?
skill builder plus, it's nitric acid reacting with sodium carbonate, and it makes water and carbon dioxide.
Okay, it's the same equation.
Yeah.
Okay, I can see where it's going now.
Okay, now, and I always organize my information underneath the chemical reaction because I think it makes it easier to go back and figure out what things are rather than reading through the text of the question. So this says, how many milliliters of sodium carbonate do I need if it's 0.112 molar sodium carbonate to completely react with 27.2 milliliters of nitric acid that is 0.135 molar concentration? Okay, so again, I'm going to start with what I have. And I have 27.2 milliliters of nitric acid. That is 0.0272 liters of nitric acid. And remember, when we're trying to figure out how much of each we need to react. Oops, I gotta admit more people. And whenever we are trying to react to chemical species or predict a product, we always need to have the moles, right? We need a mole to mole ratio. And so I'm going to use which is moles over liters, moles of solute. And so if I multiply my volume times the concentration.
Professor,
Yeah.
where you go over that again? Are those that 27.2 milliliters? Is that correct? Does that come from the problem? I don't see that in the Skill Builder Plus.
That's what oh, Skill Builder Plus, Jesus. Oops, sorry. Apparently I can only hear one word at a time.
Understand.
So you got the Skill
This
Builder?
one also, but Skill Builder Plus is what I was hung up on.
Okay, so 25 milliliters of nitric acid. Oh, okay, so this is going in the opposite. Let me see. Okay, so here's. Okay, so I have 25 milliliters of that. And I have 35.7 milliliters of sodium carbonate, and the sodium carbonate is 0.018 molar. And they want to know what is the concentration of the nitric acid. So in this case, we're not solving for volume, we're solving for concentration. And so our answer we want will be in moles over liters. Okay, so let's start with what we have. Now it's 0.0357 liters of sodium carbonate. And I have, it's 0.108 moles per liter. And so I'm going to put 0.108 moles per liter. And this is moles of Na2CO3, liters of Na2CO3. And you can see that my liters cancel. And now I have moles of sodium carbonate. Okay, and so let's see, let's calculate how many, well, let's see. Oh, and then, so now I have moles of sodium carbonate, and I need to get moles of nitric acid, but it's 1 mole of Na2CO3 per 2 moles of nitric acid. Is that? So that would be, let me calculate, 0.0357 times 0.108 times 2. So that gives me 0.0077 moles of HNO3. That's how many moles I had. And I know that that number of moles was in 25 milliliters. So if I take the moles that I have, and I divide it by the liters of nitric acid, then I have the units of molarity, and that should be the answer. And I get 0.308 molar sodium carbonate. No, where am I?
Yeah, correct.
Nitric
That's
acid. Well, that's good. Once I got to the right problem.
right. I didn't know that equation up there related to that problem. That's how I
So
come up with 2 moles of HNO3 over 1 mole of H. I see now.
yeah, so the probably the crux is remembering to use the mole-to-mole ratio, and then also that moles divided by volume will give you molarity. It's a
Yeah.
different twist on the other than on the other
Yeah.
process. Okay, well, I'm glad we got through that.
So
Sorry I was I clearly, something in my subconscious did not want to do that problem. Okay, so let's go to announcements. Let me do a different share. Okay, so day 22, May 6th. just a reminder that homework 11 on what chapter is that? Chapter 13 is due the 9th. What is that? Is that Friday? That's what day is that? I'd have to look. It's due the 9th. And we just spend one day on solutions because it's really kind of concentration and stoichiometry, which we've been doing along. And then today we start acids and bases, and that homework is due the 12th. We've got a couple, then we get another chapter that we have 2 days on again. So that gives us a little bit of a breather room. And the good thing to announce is that chapter 12, the last chapter, is more conceptual and it's a bit of review. So it's a good chapter to end the semester on. It should be, it's less quantitative and it will help you prepare for the final. On Monday, we start chapter 15, which is equilibrium. And I just wanted to note the homework 12 for the acids and bases, chapter 14. The time spent on this is long, but the 4 longest questions are practice. They're long because you have to type in chemical equations, and which take a long time and it's tedious. So I made those practice. So if you don't do them, it's not going to hurt your homework grade. However, you need to know those reactions. So I have them in there so you see what my expectations are. But I tried to take off the stress of having to type in those long things perfectly so that it accepts it. So, look at those, make sure you know those, but don't sweat it if you're getting frustrated with typing them in. Any questions on that? No questions? Okay. Have you guys done freezing point depressions yet and boiling point elevations?
Yes.
Yeah. Is that Nessa?
Yeah, I did the homework. I had to Google it a bit to figure it out, but once I figured out the constants, it was pretty straightforward.
Yeah, so maybe I'll just say a couple words about it because it's not in the slides. It's in the chapter. It's fairly simple, although people tend to make the same issue, same mistake. So this is the phenomenon. This is a phenomenon that it's called freezing point depression. Let me share my my camera again. Oh, can you guys see the camera right now?
Yes.
Yeah.
Oh, okay. I'm only now figuring out more things about Zoom. Okay, so freezing point depression. And what that means, and the other term is boiling point elevation. And honestly, those terms stick in my mind, and that's how I remember the trend, the freezing point depression. The phenomenon that you Southern Californians might not be familiar with is that in parts of the country like where I grew up, when there are icy sidewalks, you know what people do to try to get rid of the ice? It's like plow and shovel. There must be someone who grew up in cold climates. Oh, my mic is not good.
You're good now.
Yeah, it's good now.
Okay, good.
We missed your whole story.
No, I grew up on the East Coast, so I know what it's like to.
Okay, so what happens when the sidewalks get icy?
You slip and fall.
I bought my mother-in-law yak tracks. Well, what do you do to prevent the sidewalks from being icy?
You lay down salt.
Yes, you put salt. And the idea, what happens is if you have salt in water, it lowers the temperature that the water freezes to ice. So putting salt on ice melts the ice. And that is because the salt crystals disrupt the packing in the ice, and it lowers the melting point. And so at lower temperatures, you have liquid instead of slippery ice. And you can calculate the change in the freezing temperature. And it's equal to m times a constant. And that constant, this is something you have to look up. You have to be given. Oops, I'm going off screen. You have to look up this number. And for water, that number is, why is my camera doing that today? It's been doing this a lot. That constant is 1.86, and the units for it are degrees Celsius, because it's the change in temperatures, times kilograms of solvent divided by moles of solute.
Yeah, that's pretty cool.
Yeah, and what it is when ice is packed, there's this perfect crystal structure, and throwing some sodium chloride in there disrupts. It gets in the way of the perfect crystal structure. So more heat has to be released for it to freeze. Now, the other thing that's a different concept, and honestly, this is the only place I ever see molality. Little m stands for molality, not molarity. Molality. And molarity is defined, it's a little m, not a capital M, is defined as kilograms of solute divided by, moles of molality, moles of solute divided by kilograms of solvent. So you have to calculate the molality in order to be able to use this equation. And molality is always given with a little script m. So if you are given a solution, and ethylene glycol is antifreeze, and if you're given a 2.1 molal solution of antifreeze, and it's aqueous, so we'll use the constant for water. They don't give you any other values of Kf other than the one for water, so just expect to use that one. We can calculate the change in the freezing temperature. And the change in the freezing temperature will be 1.86. That's the Kf value. Degrees C times kilograms solvent divided by moles of solute times the molality, which is moles of solute divided by kilograms of solvent. And notice that my units cancel. And what I'm left with is degrees C. Okay. Why is my thing doing that? Okay, so if I calculate that, it's 1.86 times 2.1, and I get 3.9. The change in the freezing temperature is 3.9 degrees C. Now, here's where people make the mistake. This is the change in the freezing temperature. What's the normal freezing temperature of water?
0.
Yes. So the new freezing temperature is going to be 0 degrees Celsius, and this is a depression. This is how much it lowers the freezing temperature, minus 3.9 degrees C. So the new freezing temperature is minus 3.9. So you have to subtract. And when you do, it's the same kind of process for the boiling point, except for you're going to add the delta T, because it raises the boiling temperature. So for the way to remember, I remember that is when you are cooking pasta, if you put salt in your boiling water, it raises the temperature of the boiling water, because water normally boils at 100 degrees Celsius. When you put salt in it, it raises the temperature, and because it's cooking at a hotter temperature, the pasta cooks faster. So that is the phenomenon for the boiling point elevation. Okay, so that I think those two examples are pretty good for covering the parts of the solution stuff. Go ahead, if you have things that you're finding tricky, just go ahead and type in the chat or give me a shout, and I can try to describe stuff for you. Otherwise, I want to do a little bit on acids and bases today. I'm going to erase this. How's the audio now? Is it still okay?
Yes.
Okay.
Okay. Okay, so let's look at acids and bases. Yeah, let's do this. I think this is a little better. Okay, so acids and bases. Couple things about acids that you may or may not know. They taste sour, and the citric acid, which is in lemon and lime and orange, taste sour. They have the ability to grow metals, and they turn blue litmus paper to red. And these are some common acids. So where's my? Sorry, I have to find my stylus. We've worked with hydrochloric acid mainly in lab, and I think we may have had acetic acid too, which is vinegar. Hydrofluoric acid is the scary one that etches glass and goes through the skin and binds up all the sodium in your blood, and you get slow, painful death. There's some structures of acids. Bases are less common, I think, in our everyday lives. Bring up the chat. They taste bitter. They're slippery. The most common bases that I think of are a cleaner, which is a really strong one, and antacid tablets, and ammonia. And most bases contain hydroxide. Okay, so I want to get to definitions of acids and bases. So there's a couple different ways of defining acids and bases. There's what's known as Arrhenius acids and bases, and oh, now it's doing it, and Bronsted-Lowry acids and bases. For acids, Arrhenius and Bronsted-Lowry are the same molecules, but there's a little bit of a difference for bases. Let's see. Okay, so Arrhenius definition is that they produce H plus ions in solution. Sorry, I'm managing my screen here. And the base produces OH minus. And it's important to note that this is all assuming aqueous solutions. Okay, so HCl is an Arrhenius acid, and oh yeah, I'm gonna just go to camera. Okay, so HCl is an areneous acid. HCl is hydrochloric acid. When it goes into water, it separates into H plus and Cl minus. And because it produces H plus, this is considered an acid. It's worth noting that H plus does not exist alone in solution in water. What actually happens is HCl, when you put it in water, it makes H3O plus, Cl minus. The H plus, when it's freed up, always combines with water. And it makes this. This is the Lewis structure for it. So these two reactions are representing the same thing. This is more chemically correct with what's going on in more representative of the chemistry in the actual solution, but this is also just fine for representing this reaction. And sometimes it's a bit clearer to see it without the water. There are other times where you need to include the water to properly understand what's going on. Okay, so those are acids. Oh, the name of this is hydronium. This is a hydronium ion. And remember, H plus is also called a proton. Okay, now that is the areneous acid. There are also areneous bases. Areneous base, they all contain hydroxide. So anytime you see an ionic compound with hydroxide ions in it, like potassium hydroxide, when potassium hydroxide goes into solution, it separates into K plus and OH minus. And because it produces OH minus when it dissociates, this is called a base. Molecules that create hydroxide are bases. Okay, let me go back to the other window. Any questions on this stuff? Okay. So, areneous acids and bases. There I've shown the two ways to represent the dissociation of a strong acid. Sodium hydroxide is an areneous base. Now there's a different definition, and this is called a Bronsted-Lowry definition of acids and bases. And instead of producing ions, it's saying, it's looking at it from the perspective of only the proton. So an HCl is a proton donor. And so it would also meet the definition of a Bronsted-Lowry acid in addition to areneous acid. The Bronsted-Lowry definition of a base is that it's a proton acceptor. And so this definition focuses only on the transfer of H plus. So let me see. Let me go back to the camera. Okay, so potassium hydroxide is an areneous base. It's also a Bronsted-Lowry base.
We can't see the camera.
Oh, sorry, thank you. Now?
Yeah.
Okay. It's also a Bronsted-Lowry base because this hydroxide, when it's in solution, it will accept an H plus from water. And so Bronsted-Lowry base or Arrhenius bases are also Bronsted-Lowry bases, but there are some Bronsted-Lowry bases that are not Arrhenius bases. And an example of that would be ammonia. Ammonia has this Lewis structure. And when it's in water, this lone pair of electrons on nitrogen will pick up an H plus from water. And it turns out this process is reversible, so we draw the arrow in both directions. And what you wind up with is ammonium, the polyatomic ion, and hydroxide. So notice, key to the definition is that this nitrogen functioned as a proton acceptor because it took an H plus from water. But also notice that hydroxide was produced in this process. So ammonia it's a Bronsted-Lowry base, but it is not an Arrhenius base. Okay, I'm going to go back to the PowerPoint, or I'm going to try to. There. Okay, do you guys see the PowerPoint now?
Yeah.
Okay. So acids and bases always work in pairs. And what you are going to want to pick up is identifying the acids and bases in chemical reactions. So if we look at this reaction here, hydrochloric acid dissolves in water and produces hydronium and Cl minus. In this case, HCl donated a proton to water, and because it was a proton donor, it was a Bronsted-Lowry acid. The water functioned as a proton acceptor, so it was a Bronsted-Lowry base. I don't know where
I can't write on the screen because I can't find my.
Sorry guys, I don't know why. All right, so they always come in pairs. You can do other examples. So let's look at this reaction here. This is ammonia again in water. I'm gonna go back to the camera. Do you guys see the camera?
Yes.
Okay.
Yeah.
Okay. So this is an acid-base reaction. And in every acid-base reaction, there's an acid and a base on each side. We identified the ammonia as a proton acceptor. So that makes it a base. And because there's always an acid and a base on each side, this was the proton acceptor. Water functioned as a donor, right? Because it lost one of its H pluses. So water in this case was an acid. And they come in pairs on both sides. If we look at ammonia and ammonium, this is the form that has more H's. So this is the conjugate acid of ammonia. And then the two things that are most similar are water and hydroxide. The one that has more H's is the acid, the one that has less is the base. So this is the conjugate base. So in every acid-base reaction, there's a base and an acid on the reactant side. There's an acid and a base on the product side. And they come in pairs, and the pairs differ only by an H+. So if I just write my pair out, I have H3 and H4+. I have H2O, OH-. So these are acid-base pairs. They differ only by an H+, and the charge matters. You gotta add the plus. And in all cases, the form that has more H pluses is the acid. So this is the acid form, and this is the acid form. Does that make sense? So in this case, the water was an acid. In the case with, what do you guys see right now?
The PowerPoint.
Okay, let me go back. In this case, oops. Okay, so in this case, did the water donate or accept the H+?
Except.
Yeah, right. So in this reaction, water behaved like a base. Hydrochloric acid was an acid. So my acid-base pair here, this is my acid, this is my base. But notice that it's possible for water to function as an acid in a reaction, and it's also possible for it to function as a base. You have to look at what it's paired with to be able to tell the difference. And that there's a term for when something can behave both as an acid and a base, and that's called amphoteric. Okay. Go back to the PowerPoint. Okay, so water is amphoteric, and so are some of these other compounds. Sodium hydrogen sulfate, sodium disodium phosphate, monosodium phosphate, those are amphoteric. I'll get to some examples that we can look at. So here's one with bicarbonate. So in the bloodstream, the pH is maintained by a bicarbonate buffer system. This is the polyatomic ion bicarbonate. This is water. I always look at the thing that's just like this, but just has a different number of hydrogens. So I look at bicarbonate and I see this. This has more H's. So in this case, bicarbonate functions as a base because it has less protons than carbonic acid. And we usually use the term conjugate acid when it's on the product side and conjugate base when it's on the product side. And we just call it the base and the acid when it's on the reactant side. I actually don't care whether or not you use the term conjugate acid and conjugate base, but you need to be able to identify pairs. And again, here we have water, H2O. Hydroxide differs from water just by the H+. So this is the acid form, and this is the base form. And notice that I have a base and acid on the reactant side, and I have an acid and a base on the product side. Okay, so Oop, I don't want you to see that. And I can't cover it. Let's see if I can go. Do you guys see it on PowerPoint now?
Yeah.
Okay. Okay. Okay, so let's look at these two reactions. We have H2SO4 reacts with water to make H3O plus and HSO4 minus. So you want to be able to look at this and determine the pairs, the pairs of things in terms of the acid and its conjugate base. So I always do water last because it can be an acid or a base, and so I look at the things that it's surrounded by. So here I have H2SO4, and on the product side I have HSO4 minus 1. Which form is the acid form?
The H2SO4.
Yeah, okay, so this is the acid. And as long as I have this correct, water must be acting as a base. And I can check that by looking at what water is paired with on the other side. Water and hydronium here. The hydronium has more H's, so this is the acid form, the conjugate acid. So we have an acid, conjugate base. We have a base, conjugate acid. Let me see how many, and that's shown there. In this reaction in B, I have bicarbonate and water, and I have H2CO3 and hydroxide. So again, I'm going to look at water last because it's amphoteric. Turns out this could actually be amphoteric too, but I usually look at water last. I look at my bicarbonate, and over here, this one has more H's, so this is the acid form. And because it's on the product side, I'm going to call it the conjugate acid. So the bicarbonate is functioning as a base. That means the water has to be functioning as an acid. And remember, an acid is a proton donor. And this has one less H, so this is the conjugate base. There it is. Okay. I think those were the main things I wanted to get through, because I think that looking at these kinds of reactions and being able to identify the acids and bases can be tricky unless someone walks you through it. But basically what you want to look at is the acid base pairs have to be exactly the same, just differing by the number of H's. And the acid form is always the one that has more H's. And there are different kinds of reactions with acids and bases. A neutralization reaction is when you have an acid and a base, and it makes water and a salt. And the salt doesn't have to be sodium chloride, it's an ionic compound. And we use regular old stoichiometry to figure out concentrations of things. There's a process called titration. I'm trying to remember, do you guys already do that in lab? No, right?
I don't think so.
Okay. Titration is a technique where you have one thing, usually it's sodium hydroxide, where you know the concentration to a really high degree of accuracy, and you use it. You figure out exactly how much you have to add to get neutralization to figure out the concentration of the acid. And the titration, the base will be down here. And I'm sorry, the acid is down here, and the base goes into your burette. And we put a color indicator that turns just a tiny bit pink when you get to neutralization. And when the solution turns pink, that's how you know that you have evenly reacted the acid and the base. We usually have competitions to see how faint you can get the pink color, because the closer, the lighter the pink, the closer you get exactly where you have neutralized the acid. And this point where it turns pink, that's called the equivalence point. At that point, the number of moles of base that we added from here is equal to the number of moles of acid that was in the flask. And so you'll use that to calculate concentrations. I think I'm gonna stop because I think it's hard for you guys to follow, but I'll probably make a video of solving this one for you guys and post a link to it. How are you guys doing workload wise? Are you keeping up? I heard that, Bill.
Well, I do all day work on this.
All day? Well, you did well.
I did okay.
The class did well on the exam, which was good to see because you know, it's a completely different model for learning.
Professor, I had a question on the exam.
Uh-huh.
Are you gonna post like what we got wrong and what we got right on it? I'm not sure if you already did that.
No, I didn't. And I was trying to I need to ask my colleagues what they're doing about that because I think what I'll do is I'll probably open it up for a short period of time because we have to protect the exam on the digital, you know, universe. And so I don't want to open it up totally because that allows for dissemination, but I understand feedback's really important.
Yeah.
Let me ask, oh, it should say, I think on, Daniel asked what the average score was. I think there should be, when you look at the grades on Canvas, it should tell you what the average is.
You click that little window they have in the bottom right corner of it, I think.
I don't
Yeah.
remember what the average was.
And that gives you the spread from the lower, you know, the quartiles.
Okay. It seemed like it was, there were a significant number of A's, a lot of B's. A couple people struggled a little bit, but overall, I thought when you take into consideration the homework is going to lift your grade, that everybody's in good shape. So yeah, let me talk to my colleagues, but my plan would be to open up looking at the exam for like a short window of time so you could go over your answers.
Okay, that would be perfect. And one last question, on the final, is that like a cumulative of like all our exams?
Yes, the final is cumulative. We have exam 4, which will just cover the chapter since exam 3, and then we do have a cumulative final.
Okay, got it. And do you know when exam 4 will be?
I have it scheduled for May 20th.
May 20th. Okay, thank you.
Yeah, and then we have 1 day of review. So I guess, well, you guys are pretty good about asking questions. So I will just, you know, take questions, and I have to figure out how you have your exam 1 to look at. Exam 2 you have also, right? Pretty much. You have the, I'm trying to, it's all such a blur. The file, the files you uploaded, you can look at those, right? I put comments on that. So
Yeah, I think for exam 2, yeah.
So for 3 and 4 are the ones that you're gonna need to be able to look at somehow again. I'm gonna ask my colleagues what they're doing about that.
Will there be
Okay.
a practice for the final like there were for the exams?
Probably not for the final. I would say for the final, look at the practice exams.
Okay.
That's pretty much the equivalence. You know, would be that's basically where it would come from. Okay. Anything else?
Yeah, I had a question on one of the homework problems on chapter 13.
Okay.
I didn't know exactly what Pearson was looking for, and I got it all boogered up.
So is it one that's also in the book, or is it only on the homework?
Yes, it's
Okay,
it's
what number? What number is it?
476, page 476, problem 28.
Okay. Let's see.
And looking at when Pearson asked the question, they were asking for
It's that one, right? With the
yes,
pick an appropriate solvent from table 13.2 to dissolve.
yeah, they were asking for the full. I can't see the whole question. They express your answer as a. Oh man, what did they say?
You were supposed to write out the like chemical formula for each compound.
Right, and I was wondering, was I doing it wrong?
Well, for the polar ones, for the polar and ionic, it was all of the polar ones, and for the non-polar ones, it was all of the non-polar ones.
So it was full chemical equations. Like for the first one, glucose plus water goes to.
No, just the like molecular formula or
You're not writing a chemical reaction, you're just writing the formula of what gets what dissolves, right?
So for the
yeah.
first one, it would be C6H12O6. That's it.
No, it would be the ones in the table.
So for everything that's polar, did they want all of them?
Yeah.
Okay, so you would list all of these: water, acetone, methyl alcohol. For everything that's non-polar, you would list hexane, diethyl ether, and toluene.
Okay, so for example, they have glucose polar.
Yes.
Okay, no, polar has to react with polar, and non-polar reacts with non-polar.
Well,
So
not react, it dissolves.
dissolves.
Yeah.
That's what I want to say.
Mhm.
So for this first one, the answer would be water, acetone, and methyl alcohol.
Yeah.
Oh shoot!
Were you making it more complicated?
A whole lot more complicated than that. Okay, I was trying to come up with, if I had glucose and I reacted with water, what would that chemical equation, what would it go to?
Yeah.
And that's not what they want.
No, glucose would just go from being glucose solid to glucose aqueous.
Yes. Yes.
So you would essentially write, I mean, the process, if you were going to represent it as a chemical equation, would be this. And salt's
Okay.
ionic. So it would go
Okay.
from salt would be go from solid to aqueous, but it would also separate.
Like, yeah, I kind of, yeah, I know what I did. I looked up what the chemical structure of glucose was, and I put it to water, and I tried to make a full-blown stoichiometric reaction of it, but that's not what they want. Okay, so for the first one, it would just be those three polar.
But for
Okay,
vegetable oil, you would use hexane, diethyl ether, and toluene.
okay, I can work with that now because now that I understand what's going on.
Okay. Any other questions? If you're coming across problems that are tricky on the homework or in the slides and you want me to make a video, just shoot me an email and I'll make one and link to it in the PowerPoint slide. Has probably nobody's gotten to acids and bases yet.
Not yet.
No.
That's okay. You got time. But yeah, so if you are struggling with something, let me know. I like acids and bases a lot. It's a biochemical concept. Okay. Well, if there's no other questions, we can stop there. As far as the lab is pretty much set up. I'm gonna log in at 11:30. If people have questions, but I think you can just go ahead and get started if you want. Make sure you get the pre-lab done before 11:30. You're welcome.
Thank you.
You're
Thank
welcome.
you. Bye-bye.
Thank you, Professor.
Oh, my pleasure. Hang in there, guys. We're on the final slope.
It's still slippery though.
Yes, it is. But you're doing it. You're getting through it.
I guess.
And you were the first person into the Zoom today.
Yeah. All I got to do is get my days straight.
Well, did I say something wrong the other day, or were you confused which day it was yesterday?
Totally confused. I thought yesterday was Wednesday.
Okay, because I thought, did I write the wrong thing?
No, you were the right thing. My mind is a day, running behind the whole day.
I usually think Friday is Saturday, because Friday is kind of a Saturday for me, because I'm done teaching on Thursday. All right. Well, yeah, I wish I could have helped you yesterday, but you know what? It's probably better everyone got to see the problem today, because that was a different twist on most of the examples. So that was good that you asked it and we got to do it together. Okay. Well, I'm going to go. Take care.
Okay. Bye-bye.
Bye.